Okay, so today I'm going to go over what we did in class with regards to finishing up the section on solving quadratics by factoring. So our goals were to factor quadratic expressions and solve quadratic equations by factoring, and also find the zeros of quadratic functions. So at first, when we started the lesson the other day, we had talked about how foiling or using the distributive property and factoring are essentially inverse operations. So if you are to distribute or FOIL two binomials together, in this case you have x squared plus 2x plus 4x plus 8, and then that simplifies here to this x squared plus 6x plus 8. That would be how you multiply two binomials together, right? And the opposite of multiplying is dividing or factoring. So if we took our trinomial and we wanted to put it back into the form of those two binomials, that would be considered factoring, and that is the inverse operation. So x plus 4 and x plus 2 are each considered binomials because they each have two terms. The x and the 4 are each a term, the x and the 2 are each a term, and they're separated by those plus signs. Then a trinomial, here you have three terms separated by those addition signs, and that's why it's called a trinomial. So to factor a trinomial that's in the form x squared plus bx plus c, which is our standard quadratic form, we essentially have to look at the constant at the end and figure out what two numbers multiplied together to get that, and what two numbers would have to add together to get that b value or that center term. And if we think about it, when we are doing our FOILing or distributing, obviously x times x gives us this x squared, but when we multiply those two constants, that's where we get this product down here at the end. And then, of course, when we do x times n and x times m, those two coefficients will get added together to get that middle term. So the sum of those two numbers has to be equal to the middle, and the product of those two numbers would have to be equal to that constant or that c value. So let's go over some examples. So factoring each trinomial. So generally speaking, the first thing that I would always do is look at this first term and make sure there's no coefficient other than 1. So if it's just an x squared or a y squared or some variable squared, and there's no number in front other than a 1, we don't have to worry about looking for a GCF. If there was a negative there or any other number, we would want to look and see if we could divide out a GCF first, like we had done in the last set of notes. So because we do not have anything to divide out, we can immediately put our two parentheses down with the x and the x on in either one. Then we want to look at that c value or that constant at the end. You want to come up with numbers that multiply together to get 4, so factors of 4 that would then add to get 5. Okay, so we did 4 and 1, and 4 and 1 add up to get 5. Okay, so let's take a look at the next one. So for this one, again, there's no GCF in the front here, so we don't have to worry about that. So we're just going to split up the two parentheses with the x and the x because it's the only way you can get x squared. Then you're looking at your constant number here, 12. What numbers multiply to get 12 and add up to get 7? And that's 4 and 3. And in this case, they would both have to be negatives because they would have to add up to 7, but there's negative 7, so they're going to add up to negative 7. And don't worry, because when we multiply negative times a negative, we still get a positive, which we have there in front of that 12. Okay, so some more examples to go through here. So again, no GCFs on these, so we don't have to worry about dividing anything out first. The two numbers that multiply to get 36 and subtract to get 5 are 9 and 4. This is always going to go on the bigger number, that first sign, so my 9 will be positive, and 9 minus 4 gives me a 5, and 9 times negative 4 gives me the negative 36. Okay, number 4. The two numbers that multiply to get 35, that subtract to get 2. So that's kind of how I think of it in my head. This subtraction sign in front of the 35 tells me I'm going to have one positive and one negative, because when I multiply them, I need to get a negative 35. But by telling myself that they're going to subtract to get 2, that helps me figure out what those numbers are. And I know 7 minus 2 would give me, or sorry, 7 minus 5 would give me 2. So I know 7 and 5 are my numbers. Now I know one's a positive and one's a negative, but this sign here tells me which one is which. So if this sign here is a negative, my bigger number, which is 7, has to be negative, and the 5 would have to be positive, because negative 7 and positive 5 would add up to negative 2, but they would multiply to get me negative 35. Okay, so then the next 2. So again, no GCF to divide out here, so I can go right into x and x. The two numbers that multiply to get 14 and add up, since this is a plus, to get 9 would be 7 and 2, 7 times 2, and positive 7 and positive 2 add up to that positive 9. Number 6, once again, there is no GCF to divide out, so we can simply write x and x. The numbers that multiply to get 20 and add to get 12 would be what? 10 times 2 is 20, right? 10 plus 2 is 12. Now the key here is, though, it's not a positive 12, it's a negative. So I definitely know my 10 is a negative, but my 2 is also negative because I need to add up to get me that negative 12. And negative times a negative will give me that positive 20 I have at the end. All right, and then the last 2 of these simple factoring problems. So number 7, again, there is no GCF. So I'm going to go right to x and x. What numbers multiply to 27 and subtract to get 6? Well, 9 minus 3 is 6, and 9 times 3 is 27, so that combination should work. Well, if this is a positive 6, then the 9 needs to be positive and the 3 needs to be negative. And just double checking, 9 minus 3 is positive 6. 9 times negative 3 is negative 27, so that works. Now, when we go to number 8, again, there's no GCF. But here I have 2, the 2 numbers that multiply to get 2 that add to get 1. Well, this is where I run into a little bit of a problem, because if I do 2 and 1, which is the only combination that multiplies to get 2, there's no way those are going to give me a 1, because 2 and 1 don't add up to 1, they add up to 3. So I have a little problem. Some people might be like, well, why don't we just make the 2 positive and the 1 negative? But the problem with that is then you would end up with a negative 2 when you multiply those. So nothing here is going to work. So we would say that this problem is not factorable, or that is sometimes known as being a prime. So when something is not factorable, it is called a prime. Okay, so moving on to the next piece. So we talked about how to factor things that don't have the number in front of the x squared. And the other day we talked about problems where there was a number in front, but we could divide it out as a greatest common factor, or a GCF, and then we would continue the problem the way we just did those other ones. But this time we have a little bit more of a problem, because even though there's a number in front of my x squared, there's no GCF for me to divide out to get rid of it. So I can't just divide everything by 2 or something. So when that happens, you need to use the AC method. That's called the AC method because the number in front of the x squared and the constant are your A and your C, and we're going to start this problem out by multiplying them together. So my AC number is 2 times 3, which is 6. Then I'm going to ask myself what 2 numbers multiply to get 6, so the AC number, and then they're going to add up to get that middle number, which is 7. So this is where you have to think of your factors. So the factors of 6, then multiply to get 6, right? And add to get 7 would be 6 and 1. Now, this point, when we were doing simple factoring, we would just be like, oh, x plus 6, x plus 1, done. But it's not like that now because we had other numbers. This is just helping us get to where we need to go. So we're going to rewrite the problem, but instead of it as a trinomial, we're going to write it as a 4-term polynomial. So you're going to split up this middle term with the x into those 2 separate x values that we came up with over here. After we do that, and I'm going to see if I can maybe change my color here to make it a little bit easier. I'm going to take out a GCF from each half. So once you write it as that 4-term problem, you're going to then take out GCF. So what can you divide out of these? Now, most people easily can see that they're both divisible by 2, but they also both have some version of an x, so we want to divide out 2x as the GCF. Then what's left when you divide out the 2x? X plus 3. On the second side here, there's nothing that we can divide out of 1x and 3, so our GCF is simply plus 1, and the reason it's a plus is because there's a plus in the problem. If it was a minus, it would have to be a negative 1. And then we're left with x plus 3. Now, the great thing about this particular method is that once you get to this point, if these two are the same, then you know you're correct. So now my final answer here, x plus 3, will be one of those final factors, and then the two GCFs will come together, and that will be your second factor. So this would be my final answer. Now, if you wanted to, you could simply factor or FOIL or distribute to get back to that original trinomial to check your work. So if I did that, I would get 2x squared plus 6x plus 1x plus 3, and then I would see, oh yes, I did it correct. All right, so let's take a look at number 2. So for number 2, we're kind of going to do the same setup here. There is no GCF we can divide out of these 3 terms. So we're going to multiply 3 and 10 and come up with our AC number of 30. And then we're going to have to figure out what 2 numbers multiply to get 30 and add to get 17. Okay, so you might be thinking of your multiples of 30, right? So 2 and 15, 3 and 10, 5 and 6. Which of those add to get 17? So we know 15 and 2. Okay, so once you get the numbers, let's focus on the signs. We know they're going to multiply to get a positive 30, which tells us they're either both positive or both negative, but they need to add up to get negative 17, so that tells me that they both have to be negative. So once you figure out your numbers and signs, you're now going to rewrite your problem, splitting up that middle term. So we have 3x squared. Then I'm going to do minus 15x and minus 2x instead of that negative 17 plus 10. Then we're going to do our 2 GCFs. So what is my GCF of those first 2? Right here, 3x, and I'm left with x minus 5. Then on the second 2, my GCF, I can see they're both divisible by 2, but I have to take out a negative on that GCF because there's a negative in my problem. So when I divide each of these by negative 2, I'm going to get x minus 5. And that's great because we want it to be the same thing in these 2 parentheses to tell us that we're doing it correct. So now my final answer is going to be 3x minus 2. So that was just those 2 GCFs put together. And my second parenthesis would be x minus 5. Or you could switch the order if you want to write x minus 5 in the first parenthesis and 3x minus 2 in the second. It's the same thing. All right, so we got 2 more of these AC method type problems. So if I'm going to do number 3, my AC number is 4 times negative 3, which is actually negative 12. So I'm not going to worry too much about the sign right away. First, I'm going to worry about the numbers. So I need the numbers that multiply to get 12 and subtract to get 4, since there is a 4 here and a subtraction sign there, right? So that tells me one of my numbers is positive and one's negative. So the different factors of 12 are 1 and 12, 2 and 6, and 3 and 4. Which of those combinations will somehow subtract to give you a 4? 6 and 2, right? So I know I have a 6 and a 2, okay, but I need a negative 4. So is it 6 minus 2 or negative 6 plus 2, right? Which one gets the negative? So it's negative 6 plus 2. Because negative times a positive will give me that negative 12 I need when I multiply, and negative 6 plus 2 will give me that negative 4 I need when I add them up. So now I can rewrite my problem, 4x squared minus 6x plus 2x minus 3. And then I go to my two GCFs. So what's my GCF of the first two terms? Well, it looks to me like both of those could probably be divided by a 2 and also an x. So that's going to be my GCF there. And that's going to leave me with 2x minus 3. And then on the second side, I don't have anything I can divide those by. So I'm just going to have to take out a 1, and it's going to be a plus 1 because whatever sign is on that third term is what you take out on your GCF. And it's just going to be left with 2x minus 3. And that's good because it looks to me like these are matching up, right? So that's a good sign. So 2x minus 3 is one of my two parentheses, and then I can put my two GCFs together at the other. And notice this time I just did it in the other order. The order of the two parentheses isn't that important as long as you know it can be reversed, because if it's a multiple choice, who knows which way you'll write it. Okay, so let's do number 4. So number 4, we have the AC number is going to be 6 times negative 6, which is negative 36. So we need the two numbers that multiply to get negative 36 and subtract to get 5. So after some thinking about the different factors, hopefully you'll find out that 9 and 4 is the combination that you want to use there. So positive 9 minus 4 would give me positive 5, which is what I have in the middle. And 9 times negative 4 will give me that negative 36. So when I rewrite my problem, I'm using positive 9x and negative 4x in the middle. And then I'm going to do my two GCFs. So my GCF of those first two terms there is going to be 3x, and 6x squared divided by 3x is 2x, and 9x divided by 3x is 3. And then on the second side, my GCF is going to be negative 2. Now notice they're both divisible by 2, but I have this negative here on that 4x, so that's why I have to take out the negative on that 2 as well. So when I divide 4x by negative 2, I get positive 2x. Negative 6 divided by negative 2, I get positive 3, and that's fantastic because that's what we ended up in both parentheses. So my final answer is the two GCFs, which are 3x minus 2, and then 2x plus 3 is my second parenthesis. All right, and then the last thing on the factoring that we want to review is some of these special factoring patterns. So we had talked a little bit about difference of two perfect squares. So the key there is that both of your terms, your first one and your last one, have to be perfect squares. But the big important piece is that it has to be a minus sign, which is why it's called difference of two perfect squares. There is no such thing as a sum of two perfect squares. And the reason is because you have to have a negative and a positive in order for that middle to cancel. And a negative times a positive will always equal that negative. So when we go down to like number 1, for example, we have perfect square with a minus sign in the middle, and you're just splitting it up, x and x, 4 and 4, and opposite signs. Okay, now keep in mind two things. One, if you're not sure if the number is a perfect square, you can square root it on your calculator and see if it works out to a whole number. That'll tell you. The other thing is you should still be checking for a greatest common factor or a GCF to divide out first. If you don't, you're going to end up not having the fully simplified answer at the end. Okay, number 2, there is no GCF for 49 and 81, but they are both perfect squares. So I can go right to my difference of two squares pattern. The square root of 49 is 7, so I know it's going to be 7x and 7x. The square root of 81 is 9, so I know it's going to be a 9 and a 9, and then your opposite signs. Okay, number 3. Now, number 3, there's numbers in both of these, so you might try finding a GCF, but 121 is not divisible by 4 or 2, so there isn't one. So then we can go right to our pattern. 4x squared is achieved by doing 2x times 2x. The square root of 121 is 11, and then you need your opposite signs. Okay, now when we get to number 4, it's a little bit trickier Because yes, these are both perfect squares. However, they can both be divided by 9. So there is a greatest common factor here. When you divide out the 9, you get 16x squared minus 25y squared, which then you would finish using your difference of two squares pattern. So sometimes you'll see one like this. So then you have 4x plus 5y and 4x minus 5y. Now, the reason why I wanted to go over that one is because let's say you didn't notice that the 9 was a common factor, right? And you just went right away and split it up because you're like, oh, these are perfect squares. I'm just going to do 12x plus 15y and then 12x minus 15y. And then you go to look at your answer choices and you're like, oh, that answer is not there. What happened? What did I do wrong, right? Well, what happened was you'll notice that 12 and 15 have a GCF of 3. So you'd have to take out that 3, and then you'd be left with 4x plus 5y. And the same thing on the other side. You'd have to take out the GCF there, and you'd be left with 4x minus 5y. And then those two GCFs would have to get multiplied together. And then now you can see you'd have the same answer that I had by getting the GCF out first. So if you remember to take the GCF out first, it's just going to make your life easier because the numbers are smaller, and 2, your answer will be fully simplified. If you don't, then you may run into the problem that I just demonstrated there on the right. You can still get the answer, it's just a little bit more tricky. Okay, the last two problems are examples of this other pattern here, this perfect square trinomial pattern. Now, the key with this one is it's similar to the last one in the fact that your first term and your last term will be perfect squares, but the difference is the middle will not cancel out this time. You have a middle, it's actually just a double of the root of these two. So when you actually write it out, you'll notice you're getting the same parenthesis twice or the same binomial twice, so you can write it down once with a little square. Now, if you don't recognize the pattern, you just don't take the shortcut and you just do it the long way that we were doing. It's not a big deal, but if you recognize the shortcut, just save you a little bit of time. So for example, I see this is a perfect square. This is a perfect square achieved by doing 5 squared. And I know that 5 times 2 is 10, so I can just go ahead and write x plus 5, because that's a plus, and then squared. Now, let's say you didn't notice the pattern. You're like, oh, the pattern's too confusing. Well, if you just factor it the normal way, x and x, what two numbers multiply to 25 and add up to 10, 5 and 5 plus plus, you're like, hey, I got the same thing twice. You can just write it once with the squared. Same thing for number 6, okay? 8 squared is 64, and 8 times 2 is 16. So I can just write x minus 8 squared. The minus would be because of that sign right there. If you don't notice the pattern, then you can just factor it the normal way. What two numbers multiply to 64 and add up to 16? 8 and 8. Since it's a negative 16, they would both be negatives. And then you're like, hey, I have the same thing twice. You write it once with the square. And that's it for this lesson. If you have any questions, please don't hesitate to reach out.